Students, example number 3 is slightly more difficult and out of your comfort zone, and I'm going to explain a few concepts first before we start to look and assign each of these resonances to A, B, C, and D. And the first thing that I want to tell you is that when we have a double bond in our molecule, the rotation here is restricted. And because we have restricted rotation because of the pi bonds in the double bond, what you find is that each of these protons are non-equivalent. Right? Ordinarily, if I had a single bond here, the protons on here would be equivalent because of rotation around the single bond. But because the rotation is restricted, these two protons behave differently, because the C proton now sees the A proton the A protons next to it, and this B proton sees the D proton next to it on that side, and on the same carbon the B and the C see each other. So we call this coupling in a double bond. We give it certain names, and we see that the protons that are cis to each other on the same side of the double bond, these two protons B and D. So B and D would have a coupling constant, and the coupling constant is just the distance between the two peaks in Hertz. Alright, so the distance between the two peaks in Hertz. So if I have a doublet like this, the distance between that peaks there in Hertz, we give a coupling constant called J. Right, so this is given in Hertz. So in B and D, the coupling constant for cis protons on a double bond is normally about 8 Hertz. Likewise, we can see these two geminal protons. So the protons which are bonded to the same carbon, so we call them geminal. So Gemini comes from the word Gemini. So two protons on the same carbon, and B and C would have a coupling constant of around, say, 2 to 3 Hertz. Alright, so we get two types of coupling here, ortho coupling and a geminal coupling. We also get a coupling between these two protons, C and D, and that's trans to each other. So C and D, the coupling constant here is around 16 Hertz. And you can see that the coupling constant between these two protons is double the coupling constant of those two protons. So this doublet, a doublet which arises from C and D, is going to be much larger than a doublet arising from B and D. So this would be the CD coupling constant, and this would be the BD coupling constant. Right, 16 Hertz, 8 Hertz. And then a smaller coupling constant of about 2 to 3 Hertz would be your BC coupling constant. Right, so that is as if there were no other protons. So if I take this proton out from here, I'm looking at the coupling of B and C, D and C, that's what you'd get. If I take these two protons out here, I'm looking at the coupling constant of B and D, that's what you'd get here. And if I take these protons out and look at the coupling constant of B and C, that's what you'd get. And this coupling that you see here, the CH-CH2 coupling, right? So next to this CH, I have another CH2. So I also have like geminal coupling, but it's not two protons on the same carbon. So this is a normal cis coupling that you're seeing here. And you see 3-bond coupling away to the CH2, and that's the CH2 splitting there, and there's a very small coupling constant between these two protons and that hydrogen, but this gets split into a triplet. Right, so our normal 2 plus 1 n plus 1 rule, we'd split this hydrogen into a triplet. And the fact is, because these two hydrogens can now freely rotate around that bond, so this hydrogen will be split by 2 protons, and what we would get is a triplet for D. So let's see what really happens in this spectrum. So I first look at these integrations, which doesn't really help me much except for this, and you'll see that the 3 protons on the double bond are all in the region of 5 to 6. And it's in the region of 5 to 6 because we have diamagnetic anisotropy like we discussed in the lecture. Right? So all these peaks here are B, C, and D that you find here. And then this CH2 that I'm getting here, you must remember the CH2 now is next to this CH group, which would appear as a doublet. And you can find that it's also de-shielded because of the bromine atom and maybe this pi system here, but not as de-shielded as those which are attributed to diamagnetic anisotropy. So this I could attribute to A. Because it's a doublet because it's next to the CH group, and that's A. De-shielded because next to a bromine, so it occurs around 3.9. So I've got A. So these 3 resonances here must be B, C, and D, and let's see now which is which. So if I look at my C resonance, right, I would see in my C resonance what I'm actually getting is a general coupling here, a very small general coupling here, and I would also get a very large coupling that you see here. Alright, so a large coupling and a small coupling. And sometimes we don't see the very small coupling. So if I look at this region here, although I should see something between B and C, that small general coupling, and I look at the spectrum, sometimes the resolution is not good enough to give us that small coupling that I just explained to you, right? So maybe this 2 to 3 hertz was a bit over exaggerated. Sometimes actually 1 to 2 hertz as well. So it can be very much smaller than the 2 to 3 hertz. All right, so we don't see this general coupling for these 2 protons in this example. Right, so sometimes they are absent. So all we're seeing now is the cis coupling between these 2, because that's very large. And B and D would be 8 hertz, as I said, and C and D would be 16 hertz. Right, and this would be 8 hertz. So one is a bigger coupling constant and one is a smaller coupling constant. If I look at these 2 doublets here, I can see one small coupling constant and one big coupling constant. Right? So this C proton split by D must be the larger one because it's seeing now trans coupling, and this B being split by D must be the smaller one because I have cis coupling here. So this is trans coupling and that's cis coupling, and there's my trans and cis like I've showed you here. You can see one is big, one is small, one is big, one is small. Right? I don't see this general coupling in this example. If I did see the general coupling, each of these would be double doublets. 4 lines here, 4 lines here, but I don't see that. And each of these lines will be split into smaller doublets with around 2 hertz, which I don't see. Now, let's tackle D. So we know this must be D. Why is it appearing as a multiplet here with many lines? Alright, so I said initially this CH2 was split by this hydrogen into a doublet, and this hydrogen in turn is split by this CH2 into a triplet. Right, so D is split here by a triplet with a very small coupling constant. You can see the coupling constant here is very, very small, almost around here 8 hertz or so, but I think it might be around 7 hertz, not 8 hertz. But nevertheless, we do see that coupling here. And then each of these would be split into doublets by the B. Alright, so that would be a doublet, that would be a doublet, that would be a doublet. Each of these would be 8 hertz. And then split further by the C into doublets again by the C of larger 16 hertz. Can you see now there's many lines here? Alright, so that 3 would further be split into 6, and that 6 would be split into 12. So that's a multiplet that you see here. So that's why D appears as a multiplet, B and C appear as doublets. Ideally they should be double doublets, but we don't see that small general coupling, and A is a doublet because it's next to a CH group. There are certain times where you do get long range coupling from that proton to this proton, but we don't see it in this particular example.